Okay, so if you're gone today, we're looking at 4 different wave-related phenomena today. And so today's topic is on 6.2.25. We're going to look at reflection, diffraction, refraction, and total internal reflection. We do have our quiz tomorrow, so in the event that you're having to watch this remotely, be aware of that. Angle of light, incoming light ray, again, equals the angle of the reflected light ray. How it reflects depends on its texture. So we can have something called specular reflection. Specular reflection is when the surface variations are very, very small in relation to the wavelength of light. That means that light is going to maintain order. We could also have something called diffused reflection, where light is going to sort of scatter as it hits that surface. A lot of that depends on the size of the wavelength in comparison to the size of the surface variation. So occurs when surface variations are larger than the wavelength of light. Things have to be really smooth in order for visible light to be reflected specularly. Again, the idea behind this is that visible light has very, very small wavelengths. So those nanometer wavelengths there are 10 to the negative 9. So the Roy-G-Biv colors are very, very small wavelengths, which means the surface variations have to be very smooth, very small surface variations to get specular reflection. If not, it's going to scatter. I'll demonstrate that with my light box here in a few minutes. We can also have something called diffraction. So when waves encounter an obstacle or a narrow opening to pass through it, it's going to bend around it or sort of spread out. And so light can sort of bend at the interface or at that opening. Subwoofers are use this idea to be able to produce low frequency sounds. The low frequency sounds are going to spread out better from a large speaker than from a small speaker. If the wavelength is comparable to the size of the speaker, it's going to spread out some. So you would use subwoofers to produce your bass, maybe your mid-range drivers, your tweeter, and your super tweeter to do your higher frequencies. So if any of you have very good speaker systems in your home or in your car, they often have different size speakers so that you can have that sound diffract. The amount of diffraction is wavelength dependent. So the closer the wavelength is to the size of the speaker, the more it's going to spread out. Obstacles and openings that are comparable to the wavelength will produce more diffraction. So again, diffraction is a bending or a spreading out of that wave. You notice that this says it's on the project, but not on a quiz or an exam. So some of you are going to be doing, one of your project items might involve some diffraction. So it's there for you to sort of understand that as a wave principle. Reflection. There's no asterisk on that. Definitely reflection is something that could be on a quiz or an exam. Now, refraction is a little bit different than diffraction. It sounds the same. It is the bending or a change in direction as a wavefront passes from one medium into another. So now instead of it just going through an opening or around a barrier, it's just going to pass into an interface. The amount of refraction depends on both the angle of incidence, so how directly does it hit that interface or how obliquely does it hit it, and we need a change in speed. So the speed has to either increase or decrease when I go from one medium to another. To fill in these drawings here, we're going to do that after we do a little walking activity out in the hall. I'd like you to do that to help you understand refraction. You guys would all sort of be walking as wave fronts, sort of like soldiers would march in line, and then you can sort of see how that wave will change when it goes from one medium to another. Easiest to do that if we do it out in the hall. Total internal reflection is what happens when a light source or something, light passes into a medium in which speed increases. The angle of refraction would be larger. It's going to bend a certain way. There's an angle of incidence for which the angle of refraction will be 90 degrees. And so what that means is that the light would then bend right along the interface. That angle is what we call the critical angle. Critical angle is important to sort of keep that light source or that wave propagating within that medium. Anything bigger than that, and what we get is what we call total internal reflection. So the light would just sort of maintain or keep inside of that medium. So total internal reflection, the last of the 4 topics that we want to look at: reflection, diffraction, refraction, and total internal reflection. Again, this is a key part of what we call fiber optics. Binoculars will also use total internal reflection. That gives true 100% reflection. Mirrors are not able to do that. even the best mirrors are going to absorb some of that light when it hits the interface or hit that reflecting surface. If you have a pair of binoculars, oftentimes you'll see that binoculars use a series of what are called prisms here to be able to allow the light coming from a distant object to there's going to be a lens here. There's going to be a lens in the eyepiece as well as in the objective. But then what they do is a series of prisms to be able to have that light sort of spread out through here. And so those are internally reflected at that point. Of course, your eyes go here to be able to see those distant objects. Fiber optics, I think, Liam, I think if memory serves, you're going to be doing a fiber optic discussion. Is that right? Okay. So total internal reflection is the principle behind fiber optics. And so Liam will show you some more of this during his presentation. Light can be transmitted along the fiber even if it's curved. And so the idea here is that we're going to be able to keep light contained within that fiber optic cable. We can create an image, and so some of you might have used a fiber optic imaging device to be able to see maybe underneath an engine for a car. Oftentimes engines can hide a lot of view of things, and so they can snake a little fiber optic cable down through that and be able to see behind objects and underneath the engine and so forth. Information sent as pulses can be sent great distances at very large rates. And so very high rates, we can send a lot of information as a light source along a fiber optic cable. This video here is about 5 minutes. I'm going to show you that to sort of finish the day, showing you how the engineering side of a fiber optic cable, how that's made. The last thing I wanted to look at with you is just advantages of digital communication. Again, lots of slides here just to sort of finish things up. Most of today is about demonstrations and having you guys do some things with me. So the advantages of digital communication. You can have fewer errors. So when you send things digitally as a series of zeros and ones, it's very easy to detect whether or not there's noise within that, and we can determine a 0 or a 1 fairly easily, and then use an electronic system to sort of bring that back up to a 1 if we need to. If I have an analog signal where it's continuous, any noise there would be sort of hard to filter out, and it can greatly disrupt that signal. So digital, very easy to fix errors. We can send things at very high transmission rates. So as a series of pulses, we can send things along fiber optic cables with lots of what's called throughput. It's more efficient, so we can send things great distances with very little energy needs. Not easy to do that with electricity. So electricity is going to be affected by resistance along wires. Light can be sent through fiber optic cables with very little what's called attenuation. And it is more secure. In today's world, we do a lot of online banking. We do a lot of online purchasing. It's very easy to encrypt digital signals so that we can make those secure. I'd like to do a variety of demonstrations with you just so you guys can see these different wave phenomena in real life. And then I'm going to have us go do a little bit of walking out in the hallway if you'd be interested to do that with me. Hope, would you be kind enough to grab the lights for me so I can use my light box here? Okay. So these demonstrations, again, are to show you a variety of different kinds of reflections. Or a variety of different kinds of wave-related phenomena, I should say. Okay, so this is just a standard light box. It's using just a standard incandescent light, and then it's got three openings there to be able to create some parallel light rays. First thing I want to show you is just this thing called reflection. So specular reflection would look like this, where I have those 3 light rays coming in, and then since that surface of that mirror is very, very smooth, the surface variations are very small in comparison to the wavelength of light, I can have that light change its direction like so. If I were using a mirror to create an image of something, then what I would look at, if my eye was over here in this direction, I would see the image coming from this general direction here. And so we can create images from plane mirrors like so. So I would see the light coming from this direction. If I were looking in this mirror, I'd see this light box over here. And so that's where we get that mirror image. Okay, that's a specular reflection. Now the backside of this is what we call diffused reflection. And so on the backside, that the plastic is a very, very large surface variations in comparison to the wavelength of light. So you don't see any of that light coming off here. That light is diffused off of that. And so specular reflection, different than diffused reflection based on the surface variations. Now curved mirrors are able to take advantage of having the light rays be able to focus. So I can take parallel light rays, maybe coming from a distant star, or maybe it's a GPS system, or maybe a satellite cable system that's sending information to a satellite dish. Some of you might have had a satellite dish. Maybe you still have a satellite dish around your home. We're going to take those light rays there and focus them at that particular spot. So we can intensify that light and put it very intense there. If you have a satellite dish, you might notice that there is some electronics placed at the focal point. That's where that light or that radio signal is going to be intensified to be able to pick that signal up. We can also have that light spread out like so. This would create what's called a virtual image over here, where the light appears to be coming from a point behind here. Okay, so again, curved mirrors have lots of applications associated with them. I want to show you that was reflection. We also have something called refraction. So here I want to demonstrate refraction as a bending of the light at the interface. If the light comes in perpendicularly to the interface, you see it passes straight through. If I have it hit at an angle though, you can see some reflected light that's going on there, but the light is refracted at the interfaces. So here that light is bending each time it changes from one medium to another. Here the light is slowing down as it passes into that new interface. So this block, the light travels more slowly than up here. You can see it sort of bends, and then it bends like so. If I were to look through here on this side, I would see the light source sort of shifted from where it really is. And so if the object is actually here, I would see it coming from a different spot, and that's based on something called refraction. Okay, and the more obliquely we have that, the more you can see that light sort of bends. Applications of that are lenses. So some of you might have corrective lenses where you use a property of refraction to be able to make that light focus at a particular point. If you are nearsighted, if you are farsighted, you can see things far, but you can't see things up close. You would use this kind of converging lens to be able to see close-up objects. Parents, grandparents, and stuff often use a pair of reading glasses because their eyes have a hard time seeing up close. So you would use a converging lens to be able to look at up-close objects. Now, most people, especially your age, if you require glasses, it's because you can see near but not far. So you would be called nearsighted. So things that are distant from you are blurry. So here you would use a diverging lens. Diverging lenses are thinner in the middle and thicker on the edges. And so what that does is it causes the light rays to converge or diverge a little bit, creating a closer image for you. Of course, that image looks a little bit smaller. For those of you that wear glasses, you might notice that when you have the glasses on, those objects appear a little bit smaller than they do in real life, but they're clearer. And that's because you can then focus that light better on your retina. Now this is showing ideas of refraction and then total internal reflection. This is a prism, and let's say that this particular object was part of my binocular system. I could have that light completely be reflected inside of this by having it strike that interface at an angle greater than the critical angle. So all that light is then sent this way. And so again, this is the idea of total internal reflection. I do have a demonstration with fiber optics that I'll show you here in a little bit, probably with a video. But again, lots of different wave-related phenomena. I'm going to stop this video here so we can do a little bit of a walking exercise out in the hall. We do have to be somewhat quick through this because it is important for us to be able to watch that last video. So that last video is about 5 minutes. I'm going to stop the video.